Hello and welcome to the channel Neet Engine. So today we are going to be cover the topic isomerism, which is a part of organic chemistry. So let's get started. What are isomers? Isomers are such compounds which have same molecular formula but different physical and chemical properties. This Since they have same molecular formula, so the question arises, what causes this change in physical and chemical properties? This change is arise due to the difference in either their bonding pattern or difference in their 3D spatial arrangement. On such means, they can be divided into two categories: structural isomers and stereoisomers. Structural isomers are such isomers which have same molecular formula but different bonding patterns, while stereoisomers are such compounds which have same molecular formula but different in their 3D spatial arrangement. The structural isomers are further classified into six different subcategories, which are namely chain isomers, position isomers, metamerism, functional isomers, ring chain isomers, and last but not the least, tautomerism. So let's study each one in detail. Number 1, chain isomers. Chain isomers are such compounds which have same molecular formula but differs in their bonding pattern. We can understand this by taking the example of N-butane. N-butane, which contains 4 carbon atoms in a linear chain, can also form isobutane by moving one carbon from one end to second position, which results in the formation of isobutane. Both these compounds have same molecular formula C4H10, but they differ in their bonding pattern. Butane can only form these two isomers. We can understand this more by taking another example of pentane. N-pentane, which has a molecular formula of C5H12, can forms a linear chain, but it can also form isomers in which one of the carbon can move on the second position, which results in the formation of isopentane, like so. Also, another isomer can also be formed where another carbon can move from end to the second position, which results in the formation of neopentane. And hence, pentane can exist in such 3 isomers. In exam, the question may be asked based by giving a molecular formula, and you have to answer how many number of isomers such compound can form. You can solve this question either by making each structure, which can be a very time consuming process, but by learning a short trick you can solve this question within seconds. All you have to do is learn the number 2, 3, 5, 9, 18, 35, and 75, and in front of it just write C 4 5 6 7 8 9 10, and by this you get the number of chain isomer structure that a compound can form. C4 meaning butane can form only two isomer structure, and similarly C8 H18 compound can form 18 isomer structure, that is octane. So this is how you can solve the question within seconds. The second category in structure isomerism is of position isomers. Position isomers are such isomers which differs in the position of functional group, but the condition is the functional group should not contain carbon atom. This can be understood by taking the example of butene, 1 butene and 2 butene. Both these compounds have double bond but only differs in their position, and hence making it a very good example of position isomers. Another example that can be fall in this under this category is of alcohol. 1 butanol and 2 butanol. Both these functional groups does not contain carbon and hence can be classified under position isomers. The third category, which falls under structure isomers, is of metamerism. They are such isomers having same molecular formula but only differs in the groups present on the left and right side of the bridging group. This can be understood by taking the example of pentanone, sorry. This is 2-pentanone when methyl group from left side of carbonyl group is shifted on the right side, whereas the hydrogen from the right side if is shifted to the left side, it results in the formation of 3-pentanone. Hence, the groups present on the left side and the right side of bridging groups are exchanged, which results in the formation of metamerism. The example of bridging groups can be carbonyl C double bond O, COO, or of ether, etc. The fourth category of structure isomerism is of functional isomers. Functional isomers are such isomers which differs in in the position of functional group, but in this category the functional group should contain carbon atom. This can be understood by taking the example of propanol and propanone. In these example, the the hydrogen atom is shifted on the adjacent atom, while the methyl group present on the left side is moved towards the carbon. This can be understood by understanding the bond cleavage. The bond present between carbon-carbon is broken. The electrons is taken by this carbon, and the middle carbon becomes electron deficient. Sorry, the electrons present in the carbon-carbon are taken by the middle carbon, and the adjacent the peripheral carbon become electron deficient. Due to this electron richness, the electron present in the CH bond are shifted towards carbon, and hydrogen become electron deficient, which gets attractive towards this electron rich cloud, while this electron deficient methyl group is attracted towards this electron rich carbon, and shifting of bonds takes place. This proton is migrated towards the middle carbon, and the methyl group gets transferred to the other end, and hence formation of propanone takes place from propanol. In functional isomerism, the functional isomers is observed in various categories. Some of them are alcohols and ether. Alcohols gets interchanged into ether, while ether gets changed into alcohol. Aldehydes and ketones. Cyanides and isocyanides. Primary, secondary, tertiary amines also falls in the category of functional isomers. Dienes gets converted into ines. These are the examples of some functional isomers. Let's move on to the next category, that is ring chain isomers. We can understand this by taking the example of propene, double bond formed between the carbons is broken. Due to which the middle carbon becomes electron rich and the outer carbon becomes electron deficient. Due to this electron cloud, the hydrogen atom present on the adjacent carbon gets attracted towards this electron cloud and gets shifted in the middle, which results in the formation of electron deficient carbon electron rich carbon, this one will be electron deficient. This electron rich cloud and this electron deficient, these electrons get shifted in this empty orbital of carbon and a new bond is formed, which result in the formation of a ring structure called cyclopropane. In this case, in this manner, a chain form is converted into ring isomer. Now, the last category of structure isomers is of tautomerism. The essential condition for tautomerism to take place is the presence of alpha hydrogen. Now the question arises, what is alpha hydrogen? We can understand what are alpha hydrogen by taking an example. The carbon adjacent to the carbon to which a functional group is attached is known as alpha carbon. The carbon adjacent to the carbon to which a functional group is directly attached is known as alpha carbon, and the hydrogen attached to such alpha carbon are known as alpha hydrogens. Not all compounds have alpha hydrogens. For example, this is an example of new pentanol. The carbon present to the adjacent to the carbon to which functional group is directly attached is known as alpha carbon, and the hydrogen attached to such carbon are known as alpha hydrogen. In this example, you can clearly see the alpha carbon does not possess any hydrogen atom, and hence no alpha hydrogen are present in this compound. Hence, this compound cannot exhibit tautomerism. Now, what is tautomerism? In tautomerism, intermolecular proton transfer takes place. We can understand this by taking the example of propanol, in which gets converted into propanol. In this, keto form gets converted into enol form. What does enol stand for? En is derived from the en of double bond, and ol is derived from the alcohol ol, and hence which forms enol. In tautomerism, keto form gets converted into enol form. How does this conversion takes place? We can understand this by understanding the mechanism. The hydrogen, this is the alpha hydrogen gets detaches from its carbon when the electron clouds get shifted towards the carbon, and this hydrogen becomes electron deficient, which gets attracted to the lone pair of electron present on the hydrogen, and hence a bond is formed between oxygen and hydrogen. Since oxygen has formed three bonds, so a plus charge is required by the oxygen. To stabilize the oxygen, the electron from the double bond between carbon and oxygen gets shifted towards the oxygen, and the bond breaks, which results in the formation of a plus charge on the carbon. The electrons from the peripheral carbons move towards the central carbon and a bond is formed. And in this manner, a keto form gets converted into an enol form. So these were the structural isomers that we studied. The next category is of stereoisomers, which are further classified into two categories: geometrical isomerism, and optical isomerism. Geometrical isomerism, we will study both these categories in detail now. Geometrical isomerism arises due to restriction rotation around carbon double bond carbon, carbon double bond nitrogen, carbon double bond nitrogen double bond nitrogen, cycloalkanes, etc. Geometrical isomerism is also known as distereomers. Distereomers are non-mirror images. We will study this topic in detail when we'll study optical isomerism. For now, just understand that distereomers are non-mirror images. Another property of geometrical isomerism is that the geometrical isomers can be separated as they differ in physical and chemical properties. Now, what are the conditions for exhibition of geometrical isomerism? In questions are generally asked if such and such compounds exhibit geometrical isomerism or not. This can be found out easily. So now, what are the conditions that needs to be fulfilled by a compound for it to exhibit geometrical isomerism? The only required condition for any compound to exhibit GI is that each carbon should have a different set of groups attached to it. This carbon, the two groups attached to each carbon should be different. If they are same, then they cannot exhibit GI. The two groups can be similar to each other, but each carbon should contain a different set of groups for it to exhibit GI. Now, what are the different types of a GI that a compound can exhibit? There are three categories. Number one, cis trans. Number two, EZ isomers. Number three, syn anti. Let's study each one in detail now. Now, what is cis trans system? Any compound having similar groups either above or below the planes are known as cis. You can remember this. Cis stands for sister. Sister means similar, and hence if similar groups are present above or below the plane, such compounds are in their cis form, whereas the opposite of which is called trans form. If similar groups are present on the opposite sides, they are known as trans form. We will study its properties a while later. Let's move on to the next category. Category 2 is EZ system. E stands for antigon opposite, antigon opposite, whereas Z stands for Zusammen same side. Now, they can be compounds which have all four groups different to each other. So, we can't categorize them in cis or trans form. For that, we need to incorporate a new system, EZ system. Like in this example, all four groups are different to each other. So, to categorize such compounds, CIP, three scientists, develop a system to categorize them. CIP are three scientists which stands for Kant, Ingold and Prelog, and they devise some rules so as to categorize them into either E or Z category. The rules, we study the rules now. The first rule is the atom which has more atomic mass is given more priority. We can understand this by taking the example. On each carbon, the group which has more atomic mass is given more priority. On the left side carbon, out of Br and carbon, Br has more atomic mass, so it is given more priority. And on the right side carbon, between oxygen and hydrogen, oxygen has more atomic mass, so oxygen is given more priority. And since the more priority groups are on the same side, and Z is for the same side, so hence they fall in the Z configuration. Now, what if the same atoms are attached to the carbon? In such case, if the first atom attached to the carbon is same, then we will check the molecular weight of the second adjacent atom. The atom which has more weight wins the race, and while the other loses. You can understand this by taking the example. On the left side carbon, both the groups have both groups are attached via oxygen to the carbon. So we will check the next atom. The next atom is hydrogen and carbon respectively. So since carbon has more atomic weight, so we will give priority to carbon. And on the right side carbon, both the groups are attached by carbon. So we'll move on to the next atom. The next two atoms are hydrogen in both the cases. Then we'll move on to the third atom. The third atom is CH3 and hydrogen. Since carbon has more molecular weight, CH3 has more molecular weight than hydrogen, so this group wins. Since the higher priority groups are on the opposite sides, so it falls in the E configuration. Now, according to CIP rule third, if isotopes are given, then the isotope having more molecular weight is given priority. We can understand this by taking another example. T and D are the two isotopes of hydrogen. T stands for tritium and D stands for deuterium. This is 16 and this is 18 oxygen. Since this is 3 and this is 2. Since tritium has more molecular weight, so it is given more priority, and out of the 2 oxygens, 18 oxygen has more molecular weight, so it is given more priority, and the more priority groups are on the opposite ends, so it falls in the E configuration. Now there can be some examples in which carbon is attached to same atoms, but the number of bond differs, having multiple bonds. The more the number of bonds, the more priority is given, but the condition is both the atoms having multiple bonds should be the same. If unsimilar atoms are multiple bonds are present between unsimilar atoms, then the priority is given on the basis of the molecular weight. For example, carbon triple bond nitrogen is given priority over carbon double bond nitrogen, which is given priority over carbon single bond nitrogen. We can understand this by taking another example. In this, on the both sides, triple bonds are given priority over double bonds, and the high priority groups are on the opposite end, so it falls in E configuration. Since both the groups are same and are opposite ends, so it is also an example of transform. Now we'll move on to the next system, that is syn and anti-addition. Syn and anti-system. The first case is of aldoxime. This is how aldoxime is. Now, if the hydrogen and OH groups are on the same side, firstly, syn meaning same, having having groups on the same side are considered as syn, while on the opposite ends they are falls under anti category. If H and OH are on the same side, then they are termed as syn. If they are on the opposite side, then they are termed as anti. And nitrogen has one lone pair. This hydrogen and this OH groups are on the same side, so it is syn, while this hydrogen and this OH are on the opposite end, so it is anti. The next case is of ketoxime. Ketoxime. Ketoxime is represented as R1 R2 attached to carbon double bond NOH. We will understand ketoxime by taking this example. Methyl, carbon double bond nitrogen, OH. Since hydrogen is not attached to the carbon, so we can't compare OH group with hydrogen, so we need to compare it with either methyl or ethyl. If we'll compare with respect to methyl, since methyl is present in syn 2OH, so we will write syn methyl ethyl oxime. Since we mentioned the position of ethyl, so ethyl is present anti to it, it is self-explanatory. But if you want to write the answer with respect to ethyl, since ethyl is present anti to OH, so we will write anti-ethyl methyloxime. And this is how we will solve the question of aldoxime and ketoxime. Now the third case is of nitrogen double bond nitrogen. Since nitrogen has a lone pair present, so we will write with respect to lone pair. If lone pairs are present on the same side, then they are syn, and if lone pair are present on the opposite side, then they are anti, which can be understood using this example. Since lone pair are present on the same side, so it is syn, while lone pair are present on the opposite side in this compound, so it's anti. Now we will study for cycloalkanes. We also categorize cycloalkanes on the basis of the groups present above and below the plane. The necessary condition for it is there should be a sigma present between two carbon which are sp3 hybridized. If either of them are sp2 hybridized or both of them are sp2 hybridized, then they will form planar structure, and how we will explain which atoms are above or below the plane. So for us to explain the atoms above and below the plane, both the carbon should be sp3 hybridized. it can be represented in simple form like this. If similar groups are present above the plane or below the plane, then it is cis form. While if similar groups are present, same groups are present on opposite sides of the plane, then it is transform. It can also be represented using wedges, solid or dash wedges. Solid wedge represent above the plane, while dash wedge represent below the plane. If both the groups are present on the solid wedge, then it is cis form or syn form. If one group is present on solid wedge while the other group is present on the dash wedge, then it is antiform. Sorry. So these were all the systems in our syllabus. Now we will study the properties of cis and transform. The first property is that we're going to study is of dipole moment. Cis form has more dipole moment than transform. This can be understood by taking an example. Since methyl groups are electron donating, so they will donate their electrons, which will result in more dipole moment, whereas in the case of transform, the dipole moment gets cancelled. Hence, the cis form has more dipole moment than the transform. The second property is of boiling point. Boiling point is directly proportional to dipole moment. So, cis form has more boiling point than the transform. Third property is of crystal lattice energy, which is directly proportional to the stability. And as transform is more stable than the cis form, so the crystal lattice energy of transform is more than that of cis form. Fourth property is melting point, and melting point is directly proportional to the crystal lattice energy. So transform has more melting point than cis form. Next property is stability. As we discussed earlier, transform is more stable than the cis form. Next is solubility. Solubility is inversely proportional to stability. So, cis form is more soluble than transform. Is easily soluble than transform. Now, the four crystal lattice energy, melting point, stability, and solubility. These properties are as such for all compounds, while dipole moment and boiling point may differ for compounds. For example, we can understand this by taking this example. If one group is electron donating, while other is electron withdrawing group, in transform, the dipole moment does not get cancelled, it gets added, and transform has more, which results in increase of dipole moment in transform. in such example, transform has more dipole moment than cis form, and as boiling point is also directly proportional to dipole moment, so the boiling point of such example of transform is more than that of cis form. That's it for geometrical isomerism. We will study optical isomerism in our next class. Till then, bye bye.